This paper proposes a Hamiltonian to tackle the Hilbert-Pólya conjecture, focusing on eigenfunctions subject to Dirichlet boundary conditions on the positive half-line, which vanish at the origin corresponding to the non-trivial zeros of the Riemann zeta function. The eigenvalues are determined by these non-trivial Riemann zeros. If the Riemann hypothesis holds, the eigenvalues become real, representing the imaginary parts of the non-trivial zeros. Conversely, if the Hamiltonian is self-adjoint or admits only real eigenvalues, the Riemann hypothesis follows. The existence of a similarity transformation of the introduced Hamiltonian is established, which is self-adjoint on the specified domain and satisfies the eigenfunctions through the vanishing of the Riemann zeta function. This result can be extended to a broader class of functions whose zeros lie on the critical line. This approach provides a novel connection between the Riemann hypothesis and the spectral theory of a specific Hamiltonian operator. The paper's findings have significant implications for understanding the distribution of prime numbers, as the Riemann hypothesis is a fundamental problem in number theory. The proposed Hamiltonian and its properties offer a fresh perspective on this long-standing problem, with potential applications in various areas of mathematics and physics. The Riemann hypothesis, a fundamental problem in number theory, has been verified numerically for the first 1013 zeros but remains unproven. One approach to establishing the RH is the Hilbert-Pólya conjecture, which posits that the imaginary parts of the non-trivial Riemann zeros correspond to eigenvalues of a self-adjoint Hamiltonian. Berry and Keating proposed a simple, formally self-adjoint Hamiltonian, H_BK equals 1/2 x caret p plus p caret x, which matches the correct structure of the eigenvalues and provides the average number of non-trivial zeros up to a given height. However, it is still incomplete, with unclear domains for self-adjointness and boundary conditions for the vanishing of the Riemann zeta function. The Hilbert-Pólya conjecture involves two stages: finding an operator whose eigenvalues correspond to the imaginary parts of the non-trivial Riemann zeros, assuming the RH is correct, and proving that this operator is self-adjoint or admits only real eigenvalues. The latter stage is the most challenging part, requiring appropriate boundary conditions for self-adjointness. While some proposed operators have been shown to be self-adjoint, the search for a Hamiltonian that satisfies the Hilbert-Pólya conjecture continues. The authors address the Hilbert-Pólya conjecture by introducing a Hamiltonian that potentially satisfies both stages of the conjecture. In the first stage, the eigenvalues of the Hamiltonian are shown to be given in terms of the non-trivial Riemann zeros. If the Riemann hypothesis holds, these eigenvalues are real and correspond to the imaginary parts of the non-trivial zeros. The Hamiltonian, denoted as H, is built upon earlier works and is defined as a similarity transformation of the Berry-Keating Hamiltonian, involving the position operator and the number operator defined on the positive half-line. The authors define alpha equals 1 plus t, 22t, with t less than 1, and the Hamiltonian acts on the Hilbert space L2, 0, infinity. The Berry-Keating Hamiltonian is well defined and self-adjoint on the domain phi x, element of L2, 0, infinity, phi x, abs. Cont. On 0, infinity, which can be shown by comparing the dimensions of the deficiency subspaces. Both deficiency indices are equal to 0. The authors aim to demonstrate the existence of a similarity transformation that maps the introduced Hamiltonian to a self-adjoint Hamiltonian, with the corresponding domain identified by an appropriate boundary condition, which the eigenfunctions satisfy through the vanishing of the Riemann zeta function. The Berry-Keating Hamiltonian, a fundamental concept in conformal field theories and quantum optics, is unitarily equivalent to a multiplication operator. The dilatation operator, represented by d, exhibits properties analogous to the squeeze operator in quantum optics. A crucial aspect of the Berry-Keating Hamiltonian is the eigenvalue differential equation, which can be derived and solved to obtain the eigenvalues s, contingent upon the parameter s being a complex number with a real part of 1/2. This leads to a profound connection between the eigenvalues and the Hilbert-Pólya conjecture, offering valuable insights into the underlying mathematical structure. Furthermore, the eigenvalue equation for the number operator is revealed to be the Laguerre ordinary differential equation, characterized by its eigenfunctions and eigenvalues. Notably, the number operator is self-adjoint within the Sturm-Liouville framework, underscoring its significance in the context of quantum mechanics. In this section, the authors explore the eigenfunctions of the Hamiltonian, 1, in position space, denoted as psi s, x. These eigenfunctions are solutions to the eigenvalue differential equation for the Hamiltonian, subject to specific boundary conditions. The authors express these eigenfunctions using an integral and a series representation, which they identify as the generating function of Laguerre polynomials. By employing the Riemann zeta function via the Dirichlet eta function, the authors find that the eigenfunctions at the boundary satisfy the Dirichlet boundary condition only when the Riemann zeta function vanishes, leading to the eigenvalues of the Hamiltonian being expressed in terms of non-trivial Riemann zeros. S equals I, 1/2 s, s equals rho. The authors then discuss the self-adjointness of the Hamiltonian, which is crucial for ensuring that the eigenvalues are real and the eigenfunctions form a complete orthonormal basis. They argue that if the Riemann hypothesis, RH, holds true, then the Hamiltonian is self-adjoint, as the eigenvalues are all real. This result has implications for the completeness of the eigenfunctions and the possibility of a quantum system described by this Hamiltonian. The authors delve into the potential relationship between the introduced Hamiltonian and the Riemann hypothesis, RH, within the context of the Hilbert-Pólya conjecture. They investigate whether the Hamiltonian can be utilized to establish the RH by proving that it admits only real eigenvalues. To achieve this, they first emphasize that the transformation U equals T any alpha x becomes unitary when T equals a theta with theta element of R, excluding T equals 1, making the Hamiltonian a unitary transformation of the operator 1 plus x minus 1 hbk 1 plus x. This implies that the introduced Hamiltonian is self-adjoint on the Hilbert space of all square integrable functions with respect to the weight function 1 plus x squared on the interval 0, infinity. However, the imposition of the Dirichlet boundary condition may restrict the domain, potentially compromising the self-adjointness of the Hamiltonian. To address this challenge, the authors focus on the domain determined by the imposed boundary condition, psi s, 0, equals 0, while considering T, less than 1 in general. They introduce a unitarily equivalent form of the Hamiltonian, given by tilde equals a lambda d minus I lambda d, where lambda is a finite real parameter. This transformation preserves the Dirichlet boundary condition, as tilde psi s, 0, equals psi s, 0, equals 0. The Hamiltonian, 4, can be expressed as tilde equals a lambda dtn, d plus I alpha x minus I infinity sin n airy summation m equals 0 commexum, t minus ni minus I lambda d, using the series expansion of x, 1 plus e minus x, minus 1 equals infinity m equals 0 cmxm, where cm equals bm, 2m minus 1, per meter. And bm are the Bernoulli numbers with the convention b1 equals plus 1/2. Although the sum converges only for 0 less than x less than pi, it is Borel summable for all x greater than 0 and Im x less than pi. A novel formally self-adjoint operator, K, is introduced, which, together with operators D and N, forms an SU 1 algebra. This algebra is defined by specific commutation relations between these operators and the Casimir operator, C. The latter operators n plus and n are defined, enabling the identification of their action on the eigenstates of the number operator. By exploiting the SU 1 algebra, the Hamiltonian can be rewritten in a simplified form, tilde. Under the condition sh lambda equals 2t, t21, and t element of R, excluding t2 equals 1, this Hamiltonian further simplifies. By specifying t such that beta equals t21, t equals 1, the Hamiltonian takes on a form that is Borel summable under the condition beta greater than 0. The eigenvalue equation for this Hamiltonian is solved by expanding the eigenstates in the basis of the eigenstates of the number operator and then projecting onto a particular eigenstate. The resulting eigenvalue equation is expressed in terms of the coefficients fk and the eigenvalue s. The eigenvalue equation, 9, suggests that the function fk is equal to gk divided by k factorial. The function gk can be defined in terms of the Mellin transform as the integral of z to the power of k-1 times gs of z, from 0 to infinity. This formulation allows the eigenvalue equation to be rewritten as a differential equation for gs in the Mellin space. The solution to this differential equation is given by gs of z equals g0 of s times z to the power of s, e to the power of minus z, over 1 plus e to the power of z. The eigenfunctions in the original space can be obtained by expanding the eigenfunctions in the Mellin space in terms of the basis functions chi(n) of x, divided by n factorial, times the integral of z to the power of n-1, times gs of z, from 0 to infinity. The Dirichlet boundary condition can be written in the Mellin space as an integral boundary condition, which identifies the eigenvalues s as I times 1/2 minus s, in terms of the non-trivial zeros of the Riemann zeta function. This result is consistent with the analysis presented in the previous section and the boundary condition. The domain of the Hamiltonian can be elaborated via the inner product of two arbitrary states, u and v, in the Hilbert space. By expanding these states in the basis of the eigenstates of the number operator and applying the same steps as above, the inner product can be written in the Mellin space as a double integral of the product of the Mellin transforms of the states, times the modified Bessel function of the first kind, I0 of 2 square root of yz. The research introduces a similarity transformation that renders the Hamiltonian, denoted as H, self-adjoint on specified domains with appropriate boundary conditions. This transformation is manifested as a weight function in the Mellin space, identified through the mapping I0, 2 square root zy, yz, dz dy right pointing arrow omega, z, y, dz dy. The inner product is then redefined by substituting equation 12 with equation 13, where omega, z, y, equals omega, z, y, s, z, s, y. All square integrable functions can be identified in the Mellin space via equation 14. After integration by parts, equation 13 is expressed as equation 15 with a boundary term btz. The condition in equation 15 implies that z omega, z, y, is a function of z, y. Consequently, equation 16 is derived, with another boundary term bty emerging after integration by parts. By comparing equations 13 and 16, it is concluded that, in bracketly, tv, who, in bracketry, ht equals bt plus, in bracketly, 2, h of, in bracketry, ht. This analysis demonstrates the transformation of the Hamiltonian and its implications for the inner product in the context of the Mellin space. The self-adjointness of the transformed Hamiltonian, H, is achieved when the boundary term, Bt, vanishes. This boundary term is expressed as a bilinear form, and its vanishing is equivalent to the condition that the domains of H, and its adjoint, H** operator, coincide. This condition is satisfied when the limit of a specific integral expression, involving the function u, and the weight function omega, approaches 0 as z approaches 0 or infinity. Under this condition, the domains of H and H** operator become identical, ensuring the self-adjointness of the transformed Hamiltonian. The weight function omega is then identified, and the condition is shown to correspond to the Dirichlet boundary condition, psi s 0 equals 0, for the eigenfunctions g's, z. This, in turn, implies that the eigenvalues s represent the non-trivial Riemann zeros. Notably, the authors demonstrate the generalizability of their approach by replacing the operator in the Hamiltonian with an arbitrary operator w, x. This leads to a Dirichlet boundary condition involving the Mellin transform of w, suggesting that their method can be extended to a broader class of functions. Specifically, this requires a similarity transformation of the corresponding Hamiltonian, which is self-adjoint on a domain specified by an appropriate boundary condition. The manuscript introduces a well-defined Hamiltonian that could potentially satisfy the two stages of the Hilbert-Pólya conjecture. If the Riemann hypothesis holds true, the first stage involves the eigenvalues of the Hamiltonian being given by the imaginary parts of the non-trivial Riemann zeros. The second stage requires the Hamiltonian to admit only real eigenvalues, achieved through a similarity transformation making it self-adjoint on the domain where eigenfunctions satisfy the imposed boundary condition via the vanishing of the Riemann zeta function. The authors acknowledge Michael Berry and Jean Belisard for valuable discussions. The Borel sum of a given series A, x, is defined as the integral of the Borel transform BA, xt, with respect to t, where BA, xt, is the Borel transform of the series. This definition allows for the analytic continuation of the Borel sum to a larger region than the original sum converges. The authors consider the series S1, x, equals underscore, n equals 0, caret infinity lane, z, x caret n, which converges to e caret, xz, 1x, for x, less than 1. They show that the Borel sum of this series can be analytically continued to the region Re, x, less than 1. Using the integral representation of the Laguerre polynomials lane, z, equals e caret z underscore, 0, caret infinity do e caret, u caret nj0, 2 square root zoo, where j0 is the Bessel function of the first kind. The Borel sum S1, x, b, can be written as an integral of the product of two integrals. The sum inside the integral can be identified in terms of the modified Bessel function of the first kind I0, 2 square root tux. After taking the t integral, the Borel sum reads S1, x, b, equals e caret z underscore, 0, caret infinity do e caret, u, x1, j0, 2 square root zoo. The u integral converges in the region Re, x, less than 1, providing an analytic continuation of the original series. The final result is S1, x, b, equals e caret, zx, 1x, valid for Re, x, less than 1. This result demonstrates the effectiveness of the Borel summation method in extending the region of convergence of a series. The Borel sum of the series S2, x, is analytically continued to all Re, x, greater than 0 and Im, x, less than 2 pi. This is achieved by expressing the Borel sum as an integral representation involving the even Bernoulli numbers and Kelvin functions. Evaluating this integral yields an expression for the Borel sum that converges for Re, x, greater than 0 and Im, x, less than 2 pi, providing an analytic continuation of the original series. The integral representation takes the form of a contour integral in the complex plane, where the integrand involves the Kelvin functions, which are modified Bessel functions of the second kind. The even Bernoulli numbers, denoted by b2n, appear as coefficients in the integrand. The resulting expression for the Borel sum is a meromorphic function, with poles at specific locations in the complex plane. This analytic continuation enables the evaluation of S2, x, beyond its original radius of convergence. Furthermore, the section establishes a connection between the inner product in the Mellin space and the inner product in the Fourier space. This is presented through an equation that relates the two, highlighting the intimate relationship between these two spaces. This equation has significant implications for the study of analytic continuations and their applications in various fields. The calculation of the inner product of transformed eigenfunctions of the Riemann zeta function is crucial for understanding their properties in the Mellin space. The transformed eigenfunctions t psi, rho, are defined as the result of applying a unitary operator, s, to the original eigenfunctions, psr. To compute the inner product, the authors expand the transformed eigenfunctions in terms of their Fourier series, leading to an expression involving the Mellin transform of the original eigenfunctions. This allows for the identification of the coefficients in the series expansion, ultimately yielding the inner product as an integral over the Mellin space with a specific weight function, omega, z, y. In the trivial case of S equals I, the weight function omega, z, y, simplifies to I0. 2 square root zy, where I0 is the modified Bessel function of the first kind. To further simplify the integral expression, the authors introduce a new function, u, z, equals s, z, u, z, where s, z, equals z caret, z, 1 plus e caret z, resulting in a new weight function, omega, z, y, equals omega, z, y, s, z, s, y. The authors show that the transformed eigenfunctions are square integrable for non-trivial Riemann zeros, ρ, in the sense that their inner product can be expressed as a delta function multiplied by the modulus squared of a normalization constant, g0, ρ. This is achieved by employing the properties of the function f equals 12 ones, gamma, s, zeta, s, where gamma, s, and zeta, s, denote the gamma and Riemann zeta functions, respectively. The refined version. This page presents a comprehensive list of methodologies used in data analysis, including statistical models, machine learning algorithms, and data visualization techniques. It emphasizes the importance of data preprocessing and feature engineering in ensuring accurate predictions. The section on statistical models discusses the application of linear regression, logistic regression, and decision trees in various domains. The machine learning algorithms covered include neural networks, support vector machines, and random forests. Data visualization techniques such as bar charts, histograms, and scatter plots are also detailed.